so hey guys, I hope everything's going well. So what I want to do today is prove the open mapping theorem. And just looking over it and typing it up, if you notice I've got the notes on Blackboard now, and so you can look up the proof of this. This is probably one of the top two most complicated proofs we do. So I'm going to wave my hands at a couple parts, and you can look. I've tried to be as detailed as possible in the notes, and so you can look at that. But I'm just going to kind of skip over a couple parts, and you'll have to go to the notes to understand maybe some of the details of that. But so recall that the open mapping theorem, what it says, we talked a little bit about it yesterday, is that if I have a bounded operator, and by the way, these are Banach spaces. I didn't write Banach spaces, but we're working in Banach spaces from this point on. If this guy is onto, then T is an open mapping. That means T takes open sets in X to open sets in Y. What this does is it gives us information about the inverse. If you think about it, the inverse is going to be continuous if it exists. And so that's the actual injective or the bijective version of the open mapping theorem. If T is a bijection between two Banach spaces, then its inverse is continuous, hence bounded. Okay, so let's get down to the proof. All right. So what I'm going to do, find my towel here, is go through this proof. So okay, like I said, just bear with me. This is one of the most complicated theorems we prove all semester. Great that it fell in this time when we're at home, but it's fine. So first off, just a few reductions. One, this is what we're trying to prove. This is the way I like to think about the open mapping, or an open mapping in general, is we want to prove this. Well, just playing around with the definitions of open, this is equivalent to the fact that if B epsilon is a ball in X, and now if you read through the notes, I'm really careful about this. I think I'm really careful. Hopefully I didn't miss any. It's going to be a little tricky because we're going to have balls in X, and then we're going to have balls in Y. And so technically these are two different metric spaces, and so their balls are different. I'll try to note the ones in X. Like so, obviously this one doesn't need that notation because we've got this, but going through, we'll need it. Then there exists a delta greater than 0 such that there's a ball, some ball in Y centered at T of X contained in T of the image B of X. Go through the notes. I do this pretty carefully on why this works, but basically, given the open set here, I can find a ball inside of it, and this is contained in T of the open set, and hence, if I want to show that this guy's open, I want to find a ball around that. Okay, since T is linear, we can make a lot of reductions. And so for one, TB epsilon X, if you go through what this is equal to, this is just kind of pulling out constants. And remember, this is an equality of sets, okay? But it's fine. Bx plus T of X. Okay, and here this is B1 of 0. This is just a unit ball in X at the origin. Okay, and also, if I look at this side, y delta Tx, well, this is by delta 0 plus Tx. And so if I want to show that this is contained in here, basically you can technically cancel out these Tx's, and then I can divide through by epsilon. And moral of the short story is I want to show that B, and I'm going to write it delta over epsilon 0 ny is contained in t of the unit ball. Okay? So in other words, this delta over epsilon doesn't matter. It's just can be some positive number. And so the moral of the story is I want to show that given the unit ball in x, if I look at the image of t of that thing, then there exists some ball, and you can just take this to be, r, centered at the origin, contained in that image. And like I said, a lot of these calculations are because t is a linear transformation, and if you look at the way they work in terms of adding things, these are set equalities, and they're fine. Okay, so that's our goal here. Let me erase this. Okay, so let me write this here. Our goal is to show there exists an r greater than 0 such that b, r, and y of 0 is contained in t b1 x at 0. Okay, so this is what we want right here. Okay, now we can get down to it. So in x, we're going to let br. So in this proof, all the balls in x are going to be centered at the origin. So I don't want to have to write that each time. I'm going to drop the 0 here. Technically, I dropped the 0 here, but some of the balls in y are not going to be centered at the origin, so it's going to be a little tricky. So anyways, we're going to write this. And notice just because this is a vector space in the scaling, this is equal to r bx1. Okay. All right. Okay, so now notice that x is equal to the union over all these balls. And basically what this says is just if I take a set of expanding balls at the origin, every point in x is in one of these things, which just means if you're in x, your norm is finite, and so there's some n bigger than your norm. That's all that means. Okay. Now, recall what we're trying to prove. We've got the fact that t is a bounded linear operator and it's surjective. Okay. So, since t is onto or surjected, I'm going to apply t to this inequality, and it goes through the union and everything. And so what I have is that this right here is the fact that it's onto, and now this is equal to the union, n equals 1 to infinity t b x n. Okay, now here's where we're going to invoke the bare category theorem. This is the assumption is that x and y are Banach spaces, and actually it's really neat. In this proof, you're going to see we use both x and y being a Banach space. I think you can relax one of those and modify the proof a little bit, but the standard proof, both x and y are Banach spaces. Okay, so this is a countable union of sets equaling a complete metric space, and so this implies, this is by the bare category theorem, that the closure of one of these guys has a non-empty interior. And if you think about it here, well, that n just pulls out in front, and it pulls through the operator. If you check those definitions, the set definitions, it's fine. And so what this really means is, because of the linearity of t and the scaling of the balls, is that I can do this guy. You can do any ball, but it's non-empty. All right. And so this is good news. So the closure of the image of the unit ball has a non-empty interior. Okay. Now, if I could remove that closure, basically I'd be done. But I need that closure kind of plays a role in things. Okay. All right. So what can we do with this? All right. So here's where I'm going to be hand waving. This is my least favorite part of this proof, but I want to get to it. So let me get through this proof before the. By the way, if you noticed that my last video got cut off, I had started into this proof, but I realized that YouTube has a limit on the length of the videos, so I didn't finish it. So anyway, I want to finish it here. Okay. All right. So what we have right now is that the closure of this guy's non-empty. Okay, or sorry, the interior of the closure is not empty. So what that means is there exists a y0 in y and r greater than 0. So this thing's non-empty, and in its interior means I can fit a ball inside of it, such that the ball, and this is a little bit weird, but I'm going to talk about this later, of radius 4r, technically I could pick any number here, but the 4 just makes things go a little bit smoother. The ball of radius 4r, centered at y0, is contained in here. By the way, this is the ball with respect to y. It's contained in the closure. This is just the fact that the interior is not empty. There's a point in there, and then since it's in the interior, there's a little ball in it. Okay, and I picked 4r. The reason is because if you do 4r, turns out that what you can do, and this is the part I'm going to refer you to. This is actually not trivial. There's a bunch of little calculations, but I just don't want to do them here. This implies that BR0 in y is contained in TBX1, like that. Okay, and so here, notice I've reduced the radius, used some triangle inequality things, and I get that. Now, this is almost the conclusion that we want, okay? Like I said, see the notes. See notes for these calculations. They're not trivial, but I don't want to do them here. This is almost what we want. In fact, if we could just erase that closure, we would be done. However, erasing the closure takes some time. All right. Okay, so let's work with this. So now we want to remove the closure. Okay. So that's what we want to do. Okay. Well, notice one thing, I can scale this. Okay, so if I say divide by 2 on both sides, since it's a linear operator, by the way, it pulls through the closure and everything, that changes this to a ball 1/2, this to a ball of radius r/2. So notice that this scales and I'm going to leave it up to you to figure out, you know, if these little things are bothering you, go through, check the definition. This works, okay? So ball of radius r/2 to the k, ball of radius 1/2 to the k, k1, etc. All right, so now we're kind of rolling. let's do this. Okay. So, first off, we've got that BR over 2, 0 is contained in the closure T B 1/2 X, and this is Y. Okay? And by the way, this is what we're going to actually, this set right here is going to be the R we use. We get R over 2. Okay? That, in terms of the final thing, we're going to show that this is actually contained in T of B1 with the closure removed. Okay, so what does this mean? I.e., if y in y is less than r over 2, then there exists, say, a y1, and actually let me write it as an x1. There exists an x1 in x such that y minus tx1 in y is less than r over, you can double check this, 4. Okay? And by the way, this x1 is better than x. This is in b of 1/2. So, what is this saying here? Well, I'm saying if I take a y in here, it lands in here. It's in the closure of T of B of the image of the 1/2 ball. Well, that means that I can get as close as I want to y with something in T, the image of this. And so that's what I have. Okay? Now we continue this process. Now, we have that y minus tx1. What is this guy in? This is in BR 1/2 y, which will be contained in the image of B to the ball centered at 0 of radius 1/4. Okay? Let me write this. This is contained in the closure of the 1/4. Okay? So, there exists an x2 in B 1/4 such that y minus tx1 minus tx2 in y is less than r over 8. Okay, and so now you see the idea here. We're going to keep on going, getting a sum, t of x1, t of x2, t of x3, etc., where these things are, the radius here is r over 2 to the n, and the radius here, the x's are also shrinking down. Okay, so let me write the general thing, and then we'll be ready to solve it. Okay, now, let me go ahead and just erase this too so we can save some room. Continue getting x1, x2, etc., where xk is in the ball of radius 1 over 2 to the k, and y minus sum I equals 1 to k t xi, and y is less than r over 2 to the k plus 1. Okay. All right. Now, we're just about done. First off, this series infinite series, this converges in x. Why? Because if you look at the partial sums and the fact that these happen and the fact that these guys are getting small in norm and actually geometrically small in norm, that series is going to be cosine x. X is complete, hence it will converge. Converges in x since these guys, xk, in x are less than 1 over 2 to the k. Okay? And, in fact, oh, and sorry, these are strictly less than 1 over 2 to the k. And, in fact, this thing, if I use the triangle inequality, and I sum up, and by the way, that's actually strict. The triangle inequality is not strict, but these inequalities are all strict. This is 1. And so, if I let x equal this series, this guy lives in the unit ball. That's good. Okay, so I have that. And then I also have, though, the image of this series, at least in partial sums, is getting close to y. Okay, so now we are just about done. I thought I could get it on one board, but I can't. Now let's look at y. Also, t of the series, this converges in y to this guy, and this is because t is a bounded operator. Okay, that's because t is a bounded operator. So what we have is, on one hand, let's call this thing x. On one hand, we have that txk, these guys have to equal y, which recall was in our ball of r over 2, 0, y. On the other hand, this is equal to tx, i.e. what I've just shown is that if y is in the ball radius r over 2, 0, y, then y is in t ball radius 1, x. All right, because x in here is in this ball, and so y is in the image of it, i.e. this is contained, ball radius 1, no closure. That is the proof of the open mapping theorem, okay? And so what I got is, and by the way, if you just want a little picture of this, I probably should have drawn it a little bit earlier, but what's going on is maybe here's x, you've got your unit ball in there, and then we look at the image under t, maybe it does something like this, something weird. Well, what we've just done is I've found a little ball around the origin in there. And that actually, because of the linearity of t, that's all you need to show that it's open mapping. So that concludes the theorem. Like I said, I skipped some details on purpose. Look back through, look at the notes that I've posted to Blackboard, which I'm also going to add some more things to coming up soon. And look for a Zoom invitation from me probably later today or tomorrow. Take care, everyone.